Next, we are going to study about parity generation and checking. I have already given you a small idea about why parity is used, parity bit is used, and that was just for checking the errors and rectifying it if that is possible. But for this, we would for this particular example, we are going to study about only parity generation and also with checking, but not rectification. Okay, we are just only checking, we're not rectifying it. We will check, we will rectify this error in later subjects. Okay, so there are two types of parity bit, that is even parity and odd parity. I've already told you about that. And the one that we're going to discuss right now is about the even parity. Okay, and the odd parity would be just the reverse of that or the opposite of that. Okay, let's see. We have even parity generation. Okay, first of all we have to generate the parity bit. So for that, let that be, we have 3 bit of data x, y, z, and all the possible combinations are 8 possible combinations. And for that we have to generate the parity bit. Now as we are following even parity, the whole message with the parity bit should be even. That means in the whole message the number of ones should be even. So the parity bit should be such that by combining all the 4 messages, like the final message would be x, y, z, and p, by combining the message and the parity bit should contain even number of ones, and that's exactly what parity even parity means. Okay, so for that we have to use as of XOR gate. Now why XOR gate is because XOR gate is an odd function. You see, for any odd number of combination of ones, what will happen is XOR will give you 1, whereas for any even combinations like for these twos, it will give you zeros. So to generate the parity bit in case of even parity, we have to use this odd function, and that odd function is XOR. Okay, so we have followed the very same thing here. This is the logic diagram for that parity bit generation. Okay, this is logic diagram for that, and the parity bit generated accordingly is 0 1 1 0 1 0 0 1, and that's exactly the XOR of these 3 operations. You see, in this particular combination you have one as there is only single one, so you can say that XYZ is overall odd combination. So your parity bit P should be an extra one such that this whole message contains 2 ones, and that becomes an even combination, and that's exactly the even parity generation is all about. And accordingly all the other messages are also created. Okay, now there is a simple table here that shows you how to generate the parity bits here. If you are going to follow the even parity, you have to use the odd function or the XOR function to generate the parity bit. Okay, this is for generation of the parity bit. If you're going to follow the odd convention, you have to follow the even function. Now what is an even function? Just the complement of that XOR function. Okay, this is your XNOR, this is your XOR. Okay, so XNOR is for any even combination of ones, it gives you 1, whereas for any odd combination it gives you 0. This is the converse of this. Okay, so depending on what convention you follow, you're going to accordingly follow the formulas or the logic gate to give you that particular output. Okay, now as we have followed the even convention, we have to follow the XOR gate or the OR gate to generate the parity bit. Okay, now if you find, suppose there is also at the receiving end, we are going to check whether the message received is good or bad. So if checking is used, let that be, if you say that should be C, you see, for checking we have to follow the odd function or XOR function. So if you take the XOR of all four of these, what will happen if that contains even number of 1, then obviously all the output of the checking bit is going to be 0. Okay, because combining these all 4 bits, you are always going to get even number of ones, and XOR is always 0 for even number of ones. Suppose for some combination, let that be, there is an error here, let that be for this particular combination there is an error. You see, in the whole message, instead of 1, that is 0, suppose a flipping is there. For this particular combination, what will happen is your message contains odd number of ones, so your XOR value would be 1 here. So you will be notified that this particular message received is not according to the parity bit followed, or the parity generation or the checking methods followed. So you can say that the message received is wrong. Whereas if the message is not wrong or as is, whatever that is sent, that is received, you'll get 0, and you can say that the checking is done and there is no error, because all are going to be 0. For odd parity or odd parity generation and checking, the method is reverse. Wherever you use the XOR gate, you have to use XNOR, and whenever you use XNOR, you have to just flip it in case of different methods are followed. Okay, so this is about your parity generation and checking.